Hi there, this is Thermophysics Lesson 6, and we're going to look at ideal gas laws. Quite a lengthy one, quite a bit of content, but relatively straightforward. So pressure, P, you should know what this is. Pressure is force over area. Units, force is obviously newtons, area is in square meters, pressure is in pascals, and 1 pascal is 1 newton per meter square. One thing that might be useful is that standard atmospheric pressure is approximately 101 kilopascals. So you want to pause and make sure you've got that before we move on. So a quick reminder on how to convert areas. So for example, you might be given, I don't know, an area of 200 millimeters squared. And we need to convert that into square meters. So what I would do is 200 millimeters. So that would be 200 times 10 to the minus 3. And then squared. So just do that again. So times by 10 to the minus 3. Which will give us 200 times 10 to the minus 6 square meters. Let's do one more. So, I don't know, maybe if you want to practice converting that. So that would be 15 millimeters, so 15 times 10 to the minus 3, and then squared, basically do it again. So 15 times 10 to the minus 6 square meters. Then let's do one more. So what about 300 micrometers squared? So that'll be 300 micros times 10 to the minus 6, and then squared, perform that again, times 10 to the minus 6. So that'll be 300 times 10 to the minus 12 square meters. Hopefully that's okay then, let's move on. So I want you to pause, complete this table, and then I'll give you the answers. Okay, let's look. So first one, 5 pascals. Second one, 20 square meters. Third one, 400 newtons. They're really straightforward. These next ones, the units are changing, so you've got to be careful. So that's 100 kilopascals. This one, it wants the answer in millimeters squared, which is 2. And the last one, if you're not sure, pico is to the power of minus 12. So that's this one. Minus 12, micro is obviously minus 6. So you should have got 5 piconewtons, or 5 times 10 to the minus 12 newtons. Alright, let's move on. So how do gases exert pressure? So gases, you should know from GCSE, consist of molecules in constant random motion. When a molecule collides with a surface, or namely a surface of a container, or perhaps the room that you're in, impacts on the walls, it undergoes a change in momentum and it will reverse direction. Remember, normally these collisions are classed as elastic collisions, so that means that they don't lose kinetic energy. So the magnitude, the momentum as it comes back, the magnitude of the momentum would stay the same, but you've got to remember that momentum is a vector, so it'd be acting in the opposite direction, so it'd change from positive to negative or negative to positive. So here we go. So by Newton's second law and third law, the surface will experience a force from the colliding molecule. And if there's a force, the pressure exerted by the gas is equal to the total force exerted by the molecules on a specific area of the surface. So if you want to make some notes, just pause, then we'll move on. And of course, pressure is force divided by area. So experimental gas laws. So these state how the pressure, P, volume V, and absolute temperature, T, of an ideal gas relate to each other. For all of these ideal gas laws, temperature has to be in Kelvin. So real gases at relatively low temperatures and well above their condensation temperatures behave as ideal gases. So these equations work for normal circumstances. When temperatures get, very low or very, extremely high, these laws can break down. And if you do physics at university, you use this similar equations, but we had constants depending on the type of gas and the temperature that we're working at, A and B. But we don't need that at A level. So air at normal temperature is 20 degrees Celsius, and standard atmospheric pressure, what we said earlier, is 101 kilopascals. Sometimes air at normal temperature in chemistry at A level is said to be 25 degrees Celsius. But that's a good approximation to an ideal gas. Let's move on. So first one, Boyle's law. So for a fixed mass of gas at a constant temperature, PV equals a constant. Well, what that means, Boyle's law states that the pressure of a given mass of an ideal gas is inversely proportional to its volume at constant temperature. So if we keep temperature constant and they're inversely proportional, so if we doubled the volume, the pressure would halve. And if we halve the volume, the pressure will double. So the opposite will happen due to the inverse proportion. So when a gas changes pressure from pressure 1 to pressure 2, while undergoing a volume change, V1 to V2, we get an equation that looks like this. P1V1 equals P2V2. So P1V1 is the pressure and volume before the change, P2V2 is the pressure and volume after the change. And we're going to utilise that equation in a question. Remember to pause and take notes at any point. So let's have a go at this one. So a gas has an initial volume of 300 meters cubed at a standard atmospheric pressure, 100 kilopascals. Calculate the final volume of this gas if its pressure is increased by 400 kilopascals at a constant temperature. So we can use P1V1 equals P2V2, and then just put the numbers in. So pressure 1 is 100 kilopascals. I'm not going to convert it because they're both the same. Times volume 1, which is 300, equals pressure 2. So pressure 2 is increased by 400 kilopascals. So the new pressure would be 500 kilopascals. Hopefully you didn't get caught out with that. Times volume 2. So to get volume 2, we just need to do 100 times 300 divided by 500. Obviously you can see that the kilopascals would cancel out. So that leaves a volume of 60 cubic meters. Pretty straightforward. Let's move on. So pressure law. Oh, I've messed this one up. Never mind, there we go. For a fixed mass of gas at a constant volume, pressure over temperature is equal to a constant. Because the pressure law states that for a given mass and constant volume of an ideal gas, the pressure exerted on the sides of its container is directly proportional to its absolute temperature. That's at a constant volume. So if you've got, imagine a constant volume, say, I don't know, say you got I wouldn't advise this, but if you got a deodorant can and chucked it on a bonfire, what would happen? Well, it'd warm up. The volume's fixed, but because we're giving the gas inside or the liquid inside, heat energy, the pressure would increase dramatically in that instance. But it's proportional. So if you double the temperature inside the can, you're going to get double the pressure because the volume is constant. And the P1 over T1 equals P2 over T1 equals P2 over T2 is the pressure law. So let's utilize that with a quick question. So let's pause and have a go. A gas has an initial pressure of 100 kilopascals at a temperature of 27 degrees Celsius. Calculate the final pressure of this gas if its temperature is increased by 300 degrees Celsius at a constant volume. So what I'm going to do now is to go back actually and explain or recap what absolute temperature is and how to convert between. So absolute zero is the lowest possible temperature that we have in the universe. So an object at absolute zero has minimum internal energy, the absolute minimum internal energy possible. Remember internal energy, we did that the other lesson. Internal energy is the sum of the total sum of the kinetic energies and the total sum of the potential energies. So here we go. Absolute zero. There we go. Down at the bottom, 0 Kelvin is minus 273 degrees Celsius. So to go from degrees Celsius to Kelvin, we just add 273. And to go from Kelvin to degrees, we just subtract 273. And there's some examples here. Well, let's do the question. Back to it. So a gas has an initial pressure of 100 kilopascals at a temperature 27 degrees Celsius. So we need to convert that. So equation wise, we've got the P1 over T1 equals P2 over T2. So pressure 1 is the 100 kilopascals. And the temperature 1 is the 27 degrees Celsius. So we're going to add the 273 to convert into Kelvin. So that would be 300 Kelvin equals pressure 2, which is what we're going to calculate, P2, divided by temperature 2. So we start with 300 Kelvin. We add another 300 degrees Celsius, which gives us 600 Kelvin. So we need to do 100 times 600 divided by 300. Obviously, our pressure is going to give an answer in kilopascals, as our original pressure was in kilopascals as well. So 200 kilopascals is the answer. Let's move on. So last one, Charles's law. For a fixed mass of gas at a constant pressure, V over T equals a constant. So Charles's law states that the volume of an ideal gas at constant pressure is directly proportional to the absolute temperature. So as an equation, we end up with V1 over T1 equals V2 over T2. So for example, if we say doubled the volume, say we had something like this and we doubled the volume, to keep the pressures the same, so for this larger one to have the same pressure as it did initially, we would have to double the temperature as well. So that's all Charles' law is. Okay, let's move on. Quick question. A gas has an initial volume of 50 cubic meters at a temperature of 127 degrees Celsius. Calculate the final temperature required in degrees Celsius to decrease its volume to 20 cubic meters at a constant pressure. So straight away, we've got V1 over T1 equals V2 over T2. So we've got 50 divided by temperature 1. So we're starting with 127 degrees Celsius, so we need to add 273 to give 400 Kelvin, equals volume 2 is 20 divided by temperature 2. So temperature 2 is equal to, so we've got 20 times 400 divided by 50. And that gives a temperature of 160 Kelvin. But it wants it in degrees Celsius. So what we need to do is subtract 273. So the second temperature, we need to do 160 minus 273 is minus 113 degrees Celsius. Okay, let's move on. So just combine them all. So there's an equation which you can use. Very good. P1 V1 over T1 equals P2 V2 over T2. So we don't need, for calculations, you don't need to remember all those equations. We can just use this one. And a lot of the time, one of the conditions is held at a constant. So pressure might be a constant, or volume might be a constant, or temperature might be a constant, and the corresponding equation just drops out. So for example, if pressure was constant, we're left with V1 over T1 equals V2 over T2. If volumes are constant, we end up with P1 over T1 equals P2 over T2. and so on. But essentially, you just need to remember this. And then obviously I've got a big table full of questions where we can utilise this. There you go. So you've got to pause and do these, fill these in, and then I'll give you the answers. So first one, should have got 5 cubic meters. Next one, 25 Kelvin. Third one, 75 cubic meters. 400 Kelvin. Next one, pressure, 150 kilopascals. If I said Kelvin for this, that's just a mistake. Ignore that. They're all kilopascals. And last but not least, remember for this one, you've got to convert from Kelvin into degrees Celsius, so make sure you've done that. Get minus 123 degrees Celsius. So hopefully that went okay. I know it's a bit lengthy, that one, but hopefully you've got lots of useful notes and done some calculations. Thanks for watching. I'll see you at the next one.